Right, so we're doing the other one now, and what I've done is I've hooked a probe onto the damn it, I've hooked a probe onto the gate, that's the blue, and also I've hooked a probe onto the supply, which is 9 volts, and that is the green, and then the orange, this orange, which is the sorry, it's pink on here but it's orange on there, is the drain. So that's obviously the triggering. This blue is the gate, the green is the supply, which is also the source of course, and then the orange one is that. And this one, what I've done here is I've used that, I've done a subtraction between the supply and the gate, so you get the actual curve, the switching curve, because that's what it should do. Right, now that's the switch off, and you can see it's nice and smooth. Scale is 1 microsecond. So if we just turn it up a bit, no, down, that's the one. 500 nanoseconds, half a microsecond. Now, yeah, like maybe 1.5, but it's not slow. The source, on the other hand, is a little bit on the slow side. It's a bit on the sluggish side, isn't it? If I turn it like that, you can see how it's a bit wobbly, isn't it? On the source. Anyway, okay. Do the trigger, switch the slope, and we can see the other side. And again, it's a little bit noisy, but it is actually a normal gating curve. Yeah, it flattens while it charges, and then when the charge is done, it starts rising again, so it saturates. Because what I'm checking for is to see if they both saturate. Right, now look at the supply. The green one is a little bit wiggly-biddly, but when you resolve it against it, you can see that it's actually a normal curve. There's a little bit of noise, but there's a normal curve there. Yeah, isn't there? So both of these guys are switching into saturation. There is no issue there. Yeah, none. So I'm at a loss as to why this one's getting hot and that one isn't. Right, what we're getting on the gate, what voltage? Right, so the maths is 5 volts a division, so we're getting, yeah, 9 volts, aren't we? So they're both being switched using 9 volts. This one's -9 and that one's +9. So the circuit is fine, isn't it? Yeah. I don't know. So if I actually put the BLDC on, we'll see what happens. Right. Oh, it's pulled it right down, hasn't it? Look at that. I don't know. No, it's still switching the same. It is still switching the same. It's just you can't see it because of the way that the noise on the trigger is there. Right, and then let's do the other one. Okay. Yeah. The curve is the same. So it's a bit noisy, but it's not. It's still there. It's still switching. It's still saturating. What's that like? So that's cold, but that one's hot. I mean, notwithstanding, these things are actually inside plastic. That's not going to help. You know, and I'm just thinking, and the other ones are the same. And I'm thinking maybe if it has a standard TO220 case where the metal tag is out on the outside instead of having the plastic around it, then maybe it wouldn't heat up. I don't know. Maybe it's that's causing it, but I don't think so. No, because these are actually cold. You know, it's not like they're lukewarm and they're really hot. No, these are cold, and these ones are burning your fingers. So I don't get it. Doesn't make sense. The circuit works. It's possible it's due to, you know, spindly wires and stuff like that, but I don't think so. Yeah, I've put a whacking gate capacitor on here so that this supply rail, because it's a little bit distant from there, it is possible that it's due to these wires being a bit thin. You know, I need some thicker wires to transmit the power to the yeah, but as far as I can see, there's nothing wrong with that circuit. It works fine. Yeah. So I don't know, and I'm not gonna call it. It's 7 o'clock. I've got another hour, so I'm gonna just simply say the circuit works. Whatever happens is obviously a different thing. Yeah.